Now this is a kind of a latch which you can call as a 4-bit register, because 1 into 4 bit, because we have 4 latches which are being used, and this is a block diagram. Instead of representing in the individual D flip flop, you can represent in the form of this, in which we have an input buffer, we have an output buffer. Input buffer is connected with the input lines along with the write control signal, and output buffer is controlled by read signal, and the output is 0, O0, O1, O2 and O3, and this is the register which is enabled by the enable signal. In the short form also, this block diagram can be represented in this way, that we have a 4-bit register. Now this 4-bit register, meaning thereby the register can store only 4 binary digits depending upon the value of I0, I1, I2, I3, and so we will be getting O0, O1, O2 and O3. So this is an example of a 4-bit latch. Similarly, if we have an 8-bit register, then in this case there are 4. In case of 8-bit register, there will be 8 D flip flops connected all together. Now this figure shows the 4 different registers, and each register have the 8 cells, and they are arranged in a particular sequence to write into or read anything from these registers, and the specific registers must be identified by individual address, and then only it will be enabled. So for that particular purpose, we are using simple 2 to 4 decoder for decoding the address, and depending upon the value of A0 and A1, individual registers will be selected. So as I told you previously that we are in requirement of selecting the chip as well as selecting the register. Since in this particular case there is only one chip, and in that chip we have 4 registers. So first of all, whenever we have to work with any one of these registers must be identified by the address, and this address can be identified by the 2 to 4 decoder depending upon the value of A0 and A1. If the value of A0 and A1 is 0, 0, it means register 0 will work. If it is 0, 1, register 1 will work. If it is 1, 0, register 2 will work. If it is 1, 1, register 3 will work. So whenever the address is being written, first we write A1, A0. So in this way the individual, and this input buffer of this register is controlled by write signal, and output buffer is controlled by read signal. We have 8 input lines, so that we can put 8 binary digits in any one of these registers. So in this way this is going to work. Now this is an example of a 4 register, and each register can store 8 bit, so that is why it is called 4 into 8 bit. Now if you take the case of previous one, this is called 1 into 4 bit register. It means the register is, there is only one register and each register can store 4 bit. Similarly, this is signified, the chip is signified by 4 into 8. 4 significance, the significance of 4 is that there are 4 registers, and the significance of 8 is that individual register can store 8 bit. Now there is a possibility that instead of having the individual registers of 8 bit, we have only 4 bit register, meaning thereby individual register can store only 4 binary digits. In that particular case, the diagram will be like this. Then in that case, if we have to store 8 bit numbers, we are in requirement of 2 such chips, because each chip can store 4 binary digits, and we have to store 8 binary digits. So for that we are in requirement of 2 chips like that. Of course the address will remain same, A0 and A1, A0 and, because there are 4 registers and 4 registers, and these registers will be identified by the different values of A0 and A1. Of course the input buffer is enabled by write signal, output buffer is enabled by the read signal, and we have 4 input line for one register and 4 input line for the other register, and in combination it is from I0 to I7, and output will be from O0 to O7. So this is an example. If we have number of chips available, then how we are going to connect. This is another example, and this is example of 8 registers and each register can store 8 binary digits. So this is the configuration of this will be 8 into 8. Since we have 8 registers in the chip, so we are in requirement of 3 address lines to identify the individual registers, because 3 values of A0, A1 and A2 will be able to identify the individual registers depending upon the value of A0, A1 and A2. If it is 000, R0 will be selected. If it is 001, R1 will be selected. If it is 010, R2, and so on. And we have read, and this is input and the output buffer both, and this is input and the output line in combination. Now this is an example in which we have, in this case we have a one chip having 8 registers, but if we have 2 chips and each chip can have only 4 registers, how we can combine? So for that particular purpose, we have 2 chips, so individual chips has to be selected, and that is why one more term has come into the picture, that is chip select signal. So we have 4 registers in one chip, 4 registers in one chip, and so in combination we have total number of register 8, so we are in requirement of 3 address lines for identification of each. So out of this, since we have 4, so only 2 will be required to select the register. In this case also only 2 will be required to select the register. But since there are 2 chips, so one line will be required to select the chip. So we are using 2 address lines for identifying the individual registers present in the chip, but the third line will be used to select the chip individually. Now when A2 will be low, 0, when A2 will be 0, then only this chip will be selected, and this chip will be selected when this is 0. So when A2 is 0, so here you see A0, A1, and A2. So 00, 01, 10, 11, and A2 will be 000. So in that particular case, if the address is 000, R0 will be selected. If the address is 001, R1 will be selected. If the address is 010, R2 will be selected. And if it is 011, R3 will be selected. So this is memory chip 1, this is memory chip 2. Similarly, when A2 will be 1, then this chip will not be selected. When it is 1, then here it will be 0s, and this chip will be selected. So of course, for identifying these 4 registers, we are in combination, we require 0, 0, 0, 1, 1, 0 and 1, 0. But since A2 is 1, so the result will be 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So in this way, we are going to address 2 chip having 4 registers each with the chip select line. And that is why I have said earlier also, to communicate with the memory, microprocessor unit should be able to first select the chip and identify the register. And this selection of chip and identification of register requires some address lines, and combination of both address lines will be giving the binary address of the total binary address of the individual registers present in the chip. So here you can see A0 and A1 is used to select the 4 register and 4 register, but in combination with A2 it is going to give you 3-bit address. Now this is another kind of example in which we have a chip having 4 registers, and each register can have we have 4 registers and we have 2 chips of that, and we have 4 address lines. Then how we will do it? Now for selecting 4 register, 2 address lines will be sufficient. इसके अलावा rest of the address lines whichever is available, that will be connected to a logic circuit through which you are able to select the chip. So in this particular case, A2 and A3 will be used to select the chip. In this case, A2, A3 will be used to select the chip. So in this case, the chip will be selected when this will become 0. For this becomes 0, here it should be 0, here it should be 1, here it should be 1, 1, so here it should be 0. It means if A2 and A3 are 0, here it will be 1, 1, here it will be 1, but here it will be 0, so this will be the address 0, 0, 0, 0, 0, 0, 0, 0. It means when A2 and A3 are 0, 0, and a different value of A0, A1 will be going to select the R0, R1, R2 and R3. Similarly, we have M2. So we have changed the hardware design. In this case, A3 is connected directly, A2 is connected with the inverter. So the result will be A3 will be 1, A2 will be 0. So here both will be 1, 1. Here it will be 1, here it will be 0. So this chip will be selected if A3 is equal to 1 and A2 is equal to 0. So the address of the individual register will become 1000, 1001, 1010, 1011. So in this way we used to do the address. Now with this explanation we are able to know, and I am going to summarize that what are the requirement of the memory chip. Now memory chip requires address lines to identify the individual register. It also requires a chip select signal to enable the chip, and memory address of the register, any register present in the different chips, are being determined by the logic level of all the address lines, because some of the address lines will be used to identify the memory register, few of the address lines will be used to select the chip. Chip select signal will be working as a chip select signal. So combination of these two will be going to give you the memory address of the register, and the read is going to enable the output buffer and write is going to enable the input buffer. So this is just the summary of the thing which we have explained earlier. Now this is a model, the representation of the individual memory chip. One is read-write memory, another is ROM. Now the difference in between read-write memory and the ROM is, in case of read-write you can do reading process as well as writing process. That is why you are in requirement of read signal as well as the write signal. But in case of ROM we don't require to write anything because we cannot do it. So write is absent, only chip select and the RD signal is there. We have certain set of the address line which depend that how many registers are present in the memory chip. If there are 8 registers, then we are in requirement of 3 address lines. If there are 16 registers, we are in requirement of 4 address lines. If there are 32 registers, we are in requirement of 5 address lines. If there are 64 registers, then we are in requirement of 6 address lines, and like that. If we have 256 registers, then we are in requirement of 8 address lines. So depending upon that, we define the address line. Now the next important thing is that what is memory map and how the address is being assigned to the memory registers. Now as you know that memory is working simple as a notebook which we are using to write anything. Now what is the property of the notebook? Notebook is having number of pages, and each pages has number of lines. Now number of pages are also fixed and number of lines in each pages are also fixed. In a very similar fashion, we divide the total memory into number of pages and each pages having the number of registers. So in the analogy you can say number of pages in the memory and the number of pages in the notebook is same, but number of lines and number of registers available in one page is in the form of an analogous form. Now another example which I can give you, that in any housing society we have certain number of houses, and each house has its own address, has its own number by which it is being identified. So if I take an example that there is a housing society, there are 10,000 houses. So what you can do, you can assign the address of the individual houses from 0000 to 99999, so that you are able to address 10,000 houses. So if you have to find out the house number 6723, then it will be very difficult for you to find out, because if every house has been numbered in a sequence. So to find out 6723 number house, you have to go up to 67,000, then 6750, and then you are able to find out. So what we used to do in the housing society, we divide the number of houses into the sectors or the blocks, and that sector or the blocking is also used in the memory mapping also. Memory map is nothing but assigning the address of the individual register as we used to assign the address of the individual houses present in the housing society. So let me give you an example that if there are 4 digits which are used to represent a number of the house, then in that case, if we divide the total number of the houses into 100 sectors and each sector will be having 100 houses, so it means you have 10,000 houses. So out of these 4 digits, if first 2 digit represents the sector number or the block number and the rest 2 digit represent the house number, then it will be very easy to find out the individual houses. So suppose I say 6723 is the address of a house. It means 67 is the sector number 67 and house numbers 23 in that particular sector. So it is easy to identify the individual house if we divide the number of houses in a blocks or the sectors and number of house in that sector. So if you have to find out 6723, so immediately you have to go to the sector number 67 and then you have to search for the 23rd house. In a very similar fashion, memory registers are also mapped in the same fashion. The first 2 digits, because we know that there are 4 hexadecimal digits by which the individual registers are being assigned with the address, in which the most 2 significant digits represents the number of pages and the least significant 2 digits represents the number of registers present in that page, number of line present in that page. So let us see how it works. This is an example of defining the memory map of a particular chip having 256 bytes of the memory. 256 bytes of the memory means there is a one chip and that chip contains 256 registers. So to identify the 256 registers or to locate the 256 registers, we are in requirement of 8 address lines. So A0 to A7 will be assigned with the internal decoder which will be going to decode 8 into 256. Now the different combination of A0, A1, A2, A3, A5, A7 will be giving the identification of the individual registers. But we know that in 8085 we used to use 16 address lines. So only 8 address lines will be used to identify the 256 register. So what the rest of the lines will be doing? So the rest of the lines will be connected with the circuit to the chip select signal, because until unless the chip is not selected, whatever address you are going to give at A0 to A7, it is going in vain. So that is why it is necessary to select the chip with the rest of the lines, and so the address of this memory will become A0 to A15. Now how the chip will be selected? The chip will be selected if the output of this circuit will be 0. How the output of this circuit will be 0? If the input of all this will be 1. If for making the all input as 1, all the input at A8 to A15 should be equal to 0. Because if it is all will be 0, then only it will be 1, then only it will be 1, and here it will be 0, then only chip will be selected. So the address will become, what the address will become? From 1, 1, all these values will be 0, 0, 0, 0 and different values of A0 to A7. Now another circuit has been designed with a certain change in the hardware. Here the NOT gate has been removed, so A15 has to become 1. So here in this case all the value will be 0, but in this case all the value will be 0 besides the A15. A15 will be 1 and the rest will be the different values of the A0 to A7. So this is how the memory map of A. For selecting the chip, we are in requirement of all these values to be 0. For selecting the individual register, these values may be starting from 0, 0, 0 and the last value will become 1, 1, 1, 1. So the address which will be defined for this particular memory will be 0, 0, 0, 0 to 0, 0, FF. Similarly, in the second case, here A15 is 1 and the rest will be 0 and the different combination of this. So we have only one changes, that is 10000 will be the chip select or chip enable, and the register select will be from 000 to 111. So the memory map of the second figure will become 8000 to 80FFH.